Hello, my name is Haebyung Jang, a PhD student at KAIST. This talk is about new distributed learning algorithms achieving utility maximization over CSMA-based wireless multi networks. This paper is published in Proceedings of IEEE Infocom 2014. As many of you know, wireless multi networks consist of many nodes, and communications occur via multi-hop path with wireless links. Here, multiple links share the common resource, for example, the air, and some simultaneous communications are not allowed because some links within limited distance cannot use the limited resource together. This interference feature naturally leads to a question that how can we coordinate communications between links, which is a medium access control problem called MAC. A simple proposal to fix such collision problem is carrier sense multiple access called CSMA, which is from the simple idea that listen before you talk. CSMA is a practical, dominant, and popular MAC protocol used in 802.11 since it is simple and operated in fully distributed manner in the following way. In CSMA, its link tries transmission only when the medium is idle by waiting random time, and when it grabs the channel, holds some random duration. These two kinds of controlling parameters are regarded as intensity, and it determines the performance of the entire system. In recent 5 years, based on the fact that CSMA is simple and operated with no message passing, a surprising advance has been made, a new way of controlling CSMA parameters to achieve efficiency as well as low complexity in both theory and implementation community. Most researches about MAC algorithms overcoming such trade-off between efficiency and complexity are fundamentally originated from the optimization problem. Now, move our focus to see MAC problem as distributed individual control mechanisms of multi-node network. Then a game theory approach would be helpful because it is a powerful tool for the design and local control of selfish multi-agent system. In that sense, the challenge in game theoretic approach on MAC is how to design a multi-node network as a game achieving efficiency at equilibrium, and what kinds of practical, diverse game dynamics with theoretical robustness can we develop. The motivation of our work is to revisit recent utility optimal CSMA from the game-based angle and provide a different view of analysis of the system and develop some new algorithms. First, I briefly explain mathematical framework of CSMA model. A typical representation of wireless multi networks is an interference graph, where its link is a node of the graph, and interfering links are connected by edge. A schedule vector sigma represents which links are active, and for given intensity vector r, it is well known that the schedule vectors construct a reversible Markov chain with the stationary distribution proportional to the exponent of intensity of active links. Link throughput SIR is defined as an average time fraction that the link I is active, and in CSMA environment, its link can measure temporary throughput by counting the number of packets successfully transmitted, and this is an important and unique feature of CSMA, which can result fully distributed operation. In our setting, two kinds of measures are important. One is instantaneous throughput during the interval, and the other is an aggregate throughput, which is an average of cumulative throughput until that time. Now back to our goal, we now construct a non-cooperative CSMA game parameterized by beta. There are three components constructing a game. First, its link I acts as a selfish player, and second, its link I has intensity Ri as its strategy. And finally, we define a payoff function as an utility of link I subtracted by an incurring cost Ci with parameterized weight of 1 over beta. Among these three components, the choice of cost function is of critical importance. Our cost function has form of this green box, and it is different with common cost function used in many other Mac games. Actually, a common cost function reflects one link's contention impact as its aggressiveness in medium uses, Ri, multiplied by its achieved gain at the density, SIR. But our cost function more appropriately measured the link's contention impact by considering the relative increasing speed of the link's throughput during it reaches that intensity. Second feature of our cost function is that it relies only on local information. It is a function of self-strategy Ri and its throughput SIR, which can be estimated by observation in CSMA environment. These design features of cost function play a key role to have a good equilibrium, which will be explained in next slides. We use a popular concept of Nash equilibrium, where every player maximizes its payoff to analyze the equilibrium of our game. In general games, existence and uniqueness of Nash equilibrium are not guaranteed, and even if it exists, how much the entire system is efficient at the equilibrium is totally another issue. One popular metric for evaluation of efficiency of the equilibrium is the price of anarchy, defined as the ratio of maximum network utility and the aggregate utility at the Nash equilibrium. We say that a Nash equilibrium is efficient as the price of anarchy becomes closer to 1. In our game, since we smartly design a cost function, we prove that there exists a unique Nash equilibrium, and moreover, for sufficiently large beta, price of anarchy becomes 1, which means that the Nash equilibrium is efficient. Briefly, existence and uniqueness of a Nash equilibrium of our game is guaranteed because it belongs to a potential game. We can find the potential function which is strictly concave, and this unique solution exists. Moreover, we show that the potential function has the same form of the Lagrangian dual function of this approximating utility optimization problem. Since this is a convex optimization problem, by applying standard duality theory, we can prove that Nash equilibrium, which maximizes the dual function, is the solution of this approximating problem, and moreover, the objective value at the equilibrium has a gap of at most 1 over beta with that of original solution. Therefore, for sufficiently large beta, we can claim that the price of anarchy of our game becomes 1. Now, in the second part, our goal is to develop learning dynamic algorithms operating in a fully distributed manner and converging to the unique Nash equilibrium. Among many kinds of game dynamics, the most popular is the best response dynamics. In our game, best response strategy is a function of SIR. However, the exact computation of this value is intractable because it requires all other players' strategies, and the exact form of SI function is mostly unknown. Instead of calculating the exact value of SIR, we can replace it by estimated service rate by counting the number of successfully transmitted packets. Since instantaneously measured throughput is not guaranteed to have exact marginal distribution, we use aggregate service rate following a classical stochastic approximation theory. By measuring aggregate service rate, which is an average number of transmitted packets until that time, we can get sufficiently exact marginal distribution SIR after some long time. Now we propose three kinds of learning dynamics applying this approximated best response to the traditional game dynamics. Approximated version of best response dynamics selects an approximated best response as its next strategy, and second algorithm gradually moves toward the approximated best response with the smoothing factor alpha, and this is known as Jacobian dynamics. Final algorithm is an approximated gradient dynamics, which gradually updates strategy in direction of gradient of payoff. All of these algorithms require local service rate, intensity value, and change speed of local service rate. These algorithms operate in fully distributed fashion, and furthermore, each algorithm converges to the unique Nash equilibrium almost surely. The convergence is proved following the stochastic approximation theory, and I omit the detail of the proof in this presentation, and the detail is shown in the technical report of the paper. To support these theoretical results, we generate a random network topology and assume a proportional fairness of players by setting utility of its link to be logarithm function. First, we iteratively run three proposed algorithms and see that for all algorithms, intensity of its link converges to some point, and the system utility converges to one point, which is the unique Nash equilibrium. Next, we compare proposed algorithms with existing algorithms. The graph in left shows that our dynamics in green line is much faster than existing two algorithms in blue and brown lines. The graph in right shows trade-offs between efficiency of the equilibrium and the convergence speed as the value of beta grows. As we said in equilibrium analysis part, as the beta becomes large, the system utility value becomes closer to the socially optimal point, but it takes longer time to reach. This is the summary of this work, motivated by the optimization and game theoretic approach on MAC protocol. This work designed a CSMA game, provably having a unique and efficient Nash equilibrium. And moreover, we propose a new learning algorithms operating without message passing and prove that those algorithms converge to the Nash equilibrium.